Okay, thank you for the invitation. Sorry I can't be there. Some combination of teaching and kids, but hopefully this talk is still interesting. So this talk will be based on two works. The first is with me, Charles Cao, and Guanyu Zhu, and the second is with me, Aidan Chatwin Davies, Charles Cao, Gong Cheng, and Guanyu Zhu. I think Aidan is there, so if I say anything that's confusing to you, you can bother him about it because he's actually there in person. But yeah, so as the invitation said today, as the introduction said, today I'm going to focus on quantum error correction in ADS-CFT. So quantum error correction in ADS-CFT, I'm sure that you've all seen the picture before, originated by O'Mary, Dong, and Harlow, of the Q-trit code, where I divide the boundary into three regions, A, B, and C, and then the claim is that if I draw in the single party entanglement wedges, the RT surfaces here, if I have an operator X in the middle, I cannot reconstruct this operator X with any one of A, B, and C. So this was the basic realization by Ahmed, Dan, and Shidong. And it seems simple, but it actually has had rather profound consequences in the context of ADS-CFT. Thinking about things using error correction has led to strong progress in bulk reconstruction. There are several flavors of this, by Dong, Harlow, and Wall. Aaron is there. By Tom Faulkner and collaborators using more modular flow techniques, and by Patrick Hayden's group and others that are related to these techniques, various generalizations thereof. The original quantum error correcting code picture solved the so-called commutator puzzle in ADS-CFT. Where the commutator of two operators, when calculated from the boundary, looks like it's non-zero, and calculated in the bulk looks like it's zero. And so if it's an exact duality, how can this be? And the correct answer to that question is that the commutators are zero in the logical Hilbert space, but non-zero in the physical Hilbert space. And finally, but definitely not least, there's also been work that connects the ideas of quantum error correction and entanglement wedge reconstruction more generally to the arguments for proving the lack of global symmetries in ADS-CFT by Harlow and Naguri and other works. And this is very interesting because the lack of global symmetries in quantum gravity is something that is strongly believed, but until relatively recently, there have not been proofs about it. So this simple picture and the generalized quantum error correcting codes that came from it, in particular, originally the one proposed by the Happy collaboration, and further codes by Charles Cao in the Stanford group, through these different directions had a strong impact on how we understand ADS-CFT. Technical difficulties. Okay, I guess I'll figure it out in a second. There are, however, still limitations to our understanding of the holographic error correcting code. For one, holographic error correction is largely understood on time slices or space-like surfaces. If you look at the happy code or tensor networks based on quantum error correction or these sorts of things, they're often defined on time slices, and it's not clear how you go to other. It's not clear how you go to other time slices if you're starting from a single time slice. So a major problem is dynamics. There's been work by Alex May and also by Aaron, who just spoke, that constrain tensor network interpretations of dynamics. But some of these constraints are also shared by quantum error correcting code pictures. In particular, the ones that are shared are the ones where you use tensor networks in combination with quantum error correction. And so then the constraints that these people have derived on tensor networks also apply to quantum error correction. So this motivates a natural question. In some sense, it's the same natural question as what Aaron was talking about in the last talk, but I'm going to take I have a different take on it. How does quantum error correction interact with time evolution? In ADS-CFT. So I want to take a step back and say that this tension also exists in traditional quantum information, not just a holographic thing. Quantum error correction is also performed on a specific state taken as a snapshot. So the way to think about this is you have some state psi, you do syndrome detection. Once you figured out what syndrome it is, you then correct the error. Error input, you detect the syndrome, you correct the error, and then you output some psi corrected. But notably, this is also something that happens at a single instant in time, because you extract this state, you push it through, and then you essentially replace that state with this state. So this is also not a dynamical state. So there's a natural question in quantum information as to how does quantum error correction interact with dynamics in quantum information? How does quantum error correction interact with dynamics in quantum information? The answer to this is fault tolerance. So a quantum computer is said to be fault tolerant if it does not accumulate errors asymptotically This is the holy grail for quantum computing for a kind of obvious reason. As it allows scalability. In particular, you can run programs of arbitrary length without fearing corruption. So at first, this seems impossible. Your individual gates have some finite non-zero error rate. And errors accumulate multiplicatively. So your error fraction, your error rate will approach 100% at finite depth. That would be a problem, but luckily quantum information gives us a way around this. Actually, two. So the first is just normal quantum error correction. This is a way of taking your error rate and reducing it. But the second are so-called threshold theorems. Threshold theorem says that for a given quantum error correcting code, if one can correct more than 1 minus some constant fraction, the errors, where the const is bounded away from 0, then this is equivalent to being able to correct all errors. So to give you just a sense for the surface code, which is the state-of-the-art topological quantum error correcting code that people use on near-term quantum computers and won't think is the leading contender going forward. This threshold is about 10 to the minus 5 to 10 to the minus 6, which is not bad. What I mean by not bad what I mean by not bad is that the current error rate is about 10 to the minus 3 per gate. So only 3 orders of magnitude off. It's in some sense insight. Just a slight digression to say that fault tolerance is not crazy. It would be maybe crazy if the constant fraction that you needed, instead of being 10 to the minus 5 or 10 to the minus 6, was something like 10 to the minus 20 or 10 to the minus 30. Then you might think that we would never get there and this is a pipe dream, but it's not the case. And these ideas were originated in works by Aharonov and Ben Orr and have been developed by many others. So this means that in the context of ADS-CFT, there are two natural questions. First, what is the holographic manifestation of tolerance Second, what is the dual of the threshold in the threshold theorem? One exists. Holographic quantum error correction. So I will say that for these threshold theorems, these are more of an art than a science. What I mean by that is that proving specific threshold theorems for specific quantum error correction codes is not a turn the crank thing. You often need to do very specialized things to generate a threshold. It's not always clear that the thresholds that are found for specific quantum error correction codes are the best possible thresholds. And so there's a lot of work that can be done in finding better threshold theorems or making it more systematic, but that will not be the focus of what I'm talking about today. Okay, so the answer to the first question is a little trivial. It's time evolution. And specifically, it's the robustness of the metric of the space-time to back reaction from small perturbations. Why do I say that? Well, CFT states that correspond to the same bulk spacetime are in the same code subspace. And so if you have a static spacetime that's robust to small perturbations, like in GR language stays in the probe approximation, and that means that whatever things are corresponding to those small perturbations are not taking your state out of the code subspace, which is exactly what you want in quantum error correction. And if it's not taking you out of the code subspace as you evolve through time, because it's a static spacetime, then it means that that this system is in a fault-tolerant phase. Now, static spacetimes are a little bit boring. This would kind of correspond to just having a quantum computer that's not doing anything. And you just want to make sure that when the quantum information is being transmitted on the wires, while it's not doing anything, that it's not being corrupted. But we can also talk about spacetimes that are dynamical. Where the dynamics are well controlled. And they're not sourced by non-perturbative changes to the bulk spacetime. Where these would correspond to, for example, tunneling between saddle points. You can also think about these as being fault tolerant. Because now the dynamical changing of the space-time you can think of as corresponding to some quantum circuit evolution for a non-trivial quantum circuit. And you can think about tunneling between saddles as noise or corrupting information or corrupting error that would affect the validity of your calculation. And so you can also think about these as a fault tolerant phase. So this answer to the first question then motivates an approach to the second. In particular, it suggests that the bulk dual or the threshold in ADS-CFT is the Hawking-Page phase transition. So let's think about this from the picture of a bulk cartoon. First, let's consider where you're below the Hawking-Page phase transition. So then what's the bulk space-time? Well, it's vacuum ADS with some gas of gravitons in the bulk, right? That's the dominant saddle point when you're below the Hawking-Page temperature. So let's think about an ideal quantum computation, the thing that we're trying to model, as setting up a bunch of wave packets, some instant in time. They don't all have to be at the same instant in time, but for simplicity, let's say that they are, arranging them with some specific inward pointing momentum, such that they evolve, they do some scattering here. Maybe they bounce back and forth a few times because they're relativistic. And then at some later time, you measure, and that's your quantum computation. It's known that this sort of quantum billiard ball computation is universal for quantum computing, so you can model any quantum circuit in this way. And let's ask the question of what happens if you did that in this cloud of thermal ADS gas. Same thing, you arrange all the wave packets with ingoing momentum. And then now, what are the possible errors? Well, the only possible error that can happen here is deflection or scattering by the thermal gas. The metric is the vacuum metric. So if I could tune the scattering with the gravitons to 0, then this would be a very good approximation to the ideal calculation. But tuning the graviton scattering to 0 is actually a relatively good approximation to what's going on here, because the scattering cross-section with thermal gravitons in this regime is fairly low, and the density of thermal gravitons in your bulk is also fairly low. If it were higher, it would warp the geometry to be something that's not close to vacuum ADS. So small effect of scattering due to gravitons. You can calculate exactly what this is and convince yourself that it's small. But most importantly, because it's small, it's correct. Yeah, I'll get to it. Well, I guess there's no reason I can't say it now. But what corresponds to the temperature in the quantum computation is the error rate, right? So here the errors that are being generated are thermal errors. It's the same thing as if you had a superconducting wire and you heated it. then the ambient energy can make random pair productions of electrons or something in your superconducting wire, and those can generate errors in your quantum computation. So the temperature corresponds to the error rate. Did that answer your question? Are there other questions, or should I continue? So there's a small effect of scattering due to gravitons, and importantly, this is intuitively correctable. You just shift your ingoing momentum slightly. You make your wave packets deviate slightly away from the possible sources of error, or you just ignore it, and this is intuitively correctable. So this feels intuitively fault tolerant. I'll give a better argument for why it's fault tolerant later, but the bulk cartoon is intended to suggest to you first why this is not a crazy idea. Well, that this part isn't crazy. Feels fault tolerant. Okay. So if I'm saying that there's a threshold here, that means that if I go to the other side of the phase transition, it's going to not feel fault tolerant. So what happens if I go above HP? So again, the idealized system that I'm trying to do is scattering in vacuum ADS with these ingoing wave packets. At some time they scatter, and then I measure at some late time. But above the Hawking page phase transition, the metric does non-trivially change. And it non-trivially changes in a particularly difficult way. So in particular, there's now a black hole in the middle of your space-time. And outside of 3D gravity, the metric warps in a way such that it's not particularly well approximated by the vacuum solution anymore, even outside the person. So this is a problem, because now if I try to do exactly the same thing, I have ingoing wave packets, some order 1 fraction of the wave packets will fall into the black hole. Right? So some order 1 fraction will fall into the black hole, and you say, okay, that's fine. Some person says this. Just do Hayden Fresco to recover. And that's true. So Hayden Fresco, if I wait long enough, lets me recover info from dropped into the black hole. If I wait until after the page time. But I want to argue that this is inherently not very compatible with fault tolerance, with the state being fault tolerant. So in particular, if a quantum computer is fault tolerant, then Nielsen and Twang, Wikipedia, whatever you want to look at, tells me that, says that I can simulate P of n gates, where P is just some polynomial, using order of P of n times some polylogarithmic function of P of n, or n, whatever you like, gates. Without accumulating error. But this is precisely what you can't do. Prevents you from doing this. Hayden-Preskill specifically makes it such that the overhead that you get will be greater than a polylogarithmic overhead factor. Because Hayden-Preskill, the time that it takes to run that thing depends on the number of qubits that are both associated with the black hole and the number of qubits in your message that you throw in. And if you use like the arguments by Daniel and Patrick, this is some QSEK card thing. So it takes a very, very long time in order to actually perform this protocol to extract information that you drop into the black hole. And to convert it into some useful form, to descramble it, if you like. So Hayden-Preskill prevents you from satisfying this condition. And so this means that when you have a black hole and you drop some of the information into the black hole in ADS-CFT, you're now naturally in a not fault-tolerant phase. And this is not just something that you feel, or I feel. This is something that you can show. Because we understand the physics of black holes and scrambling well enough to make this statement precise. So then, let's summarize what this cartoon picture says. This cartoon picture suggests that there is a good reason to associate fault tolerance with the Hawking-Page phase transition. I'm realizing now that it's particularly unfortunate that Hayden-Preskill and Hawking-Page have the same acronyms, but you'll have to bear with me. And when I use HP, try to use context clues to figure out what it is, or ask me if you're unsure. Okay, so the main thrust of the work that I did with Charles and Guan Yu, of note, Guan Yu is at IBM, so it's funny that he had to write a paper on black holes, but he cared about it, so he did. You can prove the feeling that below the Hawking-Page phase transition, you're in a fault-tolerant phase using CFT calculations in certain limits. In an upcoming work by Charles's postdoc Gong Cheng, you can prove the statement from the bulk directly. So that's what we did. But there's some more things that I want to say about the connections here, which is that the Hawking-Page dual it already had a boundary dual. It already had a boundary dual that was independent of quantum information. Specifically, the Hawking-Page phase transition is believed to be dual to the confinement-deconfinement phase transition. Now, this is up to caveats that have been pointed out by, for example, Marsano, Van Ramstonk, others, where they point out that the precise location of the confinement-deconfinement phase transition in the CFT and the Hawking-Page phase transition are slightly offset from each other, but by a constant amount. So while there is a connection, they're not precisely overlaid on top of each other. but I'm going to move past that statement for now for the purposes of what I'm saying. And this suggests a close connection between your confinement-deconfinement phase transition and threshold theorems. For holographic quantum error correction. So, in other words, your duality is secretly a triality. Or that these two things that you're talking about on the boundary are secretly just the same thing, looking at the CFT in two different lenses. So this might seem kind of random, but it's actually kind of amazing. Because this connection between the confinement-deconfinement phase transition and threshold theorems for quantum information science has actually been studied before in a completely different context. So in the context of topological quantum error correcting codes, you can think about Z2 gauge theory, the toric code, surface code, code, all sorts of quantum error correcting codes that are based on topological quantum field theory, or topology. In this context, there was a work, I think in the early 2000s, by Dennis Kitaev, Landau, and Preskill. And these guys argued that the threshold for topological quantum error correcting codes of specific types is set by the confinement-deconfinement phase transition. So this is a proven result. And for us, this is something that's suggested by conjectured dualities between the confinement-deconfinement phase transition in Hawking-Page, which is on fairly solid ground in ADS-CFT, and the work that we did connecting the Hawking-Page phase transition to the threshold theorem in quantum information. So we now have two points, if you like, in theory space, where there's a connection between confinement-deconfinement phase transitions and threshold theorems, which is kind of interesting because holographic CFTs are in many ways opposite to TQFT. In some sense, you can think about a line like a path through theory space where TQFTs live on one end of the path and holographic CFTs live on the other end or close to the other end of the path. And now at both ends, we find there's a connection between confinement and deconfinement. I won't draw a double-sided arrow because that's too suggestive, but there's a connection between confinement, deconfinement, and threshold theorems. So this now motivates another natural question. Possibility, conjecture, however you want to say it, which is that all QFTs that confine have a quantum error correction interpretation. And indeed have a threshold that by the confinement deconfinement phase transition. So if this is true, then what it could do is it could allow quantum error correction techniques, which have already proven to be quite fruitful in the restricted context of ADS-CFT, to be brought to bear studying confining field theories, or even for deciding if a field theory is confining. What I mean by that is that if you can somehow prove that a quantum field theory either cannot have a non-trivial quantum error correction interpretation, or that it cannot have a non-trivial threshold, then if this conjecture is true, then that might allow you to say that that quantum field theory cannot be confined. So extremely optimistically, this might even allow a different perspective on the mass gap problem, where maybe by thinking about things in terms of what kinds of errors you can correct or cannot correct as you accumulate errors, maybe only after accumulating a certain amount of errors, where each error has some energy associated with it, can you transition from a confining phase to a deconfining phase? And the amount of error you need to accumulate is what sets the mass gap. That could be a way of thinking about this using quantum error correction language. So as you can see, this is a direction that is potentially very interesting to look at. So having said that, I'm going to follow suit with what Aaron did and say that we also have not solved this problem. Using his language, perhaps this will dampen your enthusiasm, but it's clearly an interesting question to look at. But we have made progress on a related problem. Related problem that we've looked at is to make another connection between high energy physics, or I guess just physics, and quantum error correction via superselection sectors. So we can show that every superselection sector the existence of superselection sectors implies the existence of a quantum error correcting code. And in particular, this implication is because superselection sectors imply the validity of the Canil-Laflamme condition. For quantum error correction. And the KL conditions are sufficient for a quantum error correcting code to exist. So this is kind of intuitive. A superselection sector. Superselection says that there does not exist an operator that can take a specific state psi to some other specific state phi. In some sense, you can think about superselection rules as some statement about the block diagonality or approximate block diagonality if you have approximate superselection of the unitaries that govern your dynamics. But this is precisely what you want in quantum error correction, right? So these blocks in superselection, we can call these the code subspaces. And the operators that you have can move you around inside a specific code subspace, but are prevented from taking you from one code subspace to another code subspace. And then you can ask, well, if that's the case, isn't this too good? What are the logical operators? These logical operators are always, for for example, high energy operators that break superselection. So superselection rules are almost always EFT statements, which means that they apply when you consider operators that are in some certain energy window. But if you have operators that are outside the energy window, you can clearly break it. A good example to keep in mind is QCD. One of the reasons why I started thinking about superselection first is in order to make progress on this confinement deconfinement question. In QCD, if I'm in the phase where my quarks have hadronized into protons and neutrons, then there does not exist low energy operators that can exchange a quark that's in one proton with a quark that's in another proton. But if I keep my system above lambda QCD, where the system is now no longer its fault tolerant phase and the quarks are now free, then of course I can make these exchanges. And so you have superselection when you're in the phase where everything is hadronized, and you do not have superselection once you go above. So in this work, this was some work by me, some of the same people, Charles Cao, his student Gong Cheng, Hayden Chatwin Davies, and Guanyu Zhu again, making this connection between superselection and quantum error correction. We also discussed schematically, in some cases and in detail in others, how this applies to certain cases certain famous cases where superselection exists. For example, QCD, or a simple model of QCD, supersymmetric quantum field theories, and TQFTs. This audience, maybe I'll say a few words about supersymmetric field theories. It's commonly understood that the more supersymmetry your system has, the more restricted the dynamics that your system can obey are. So in some sense, you can think of that as being when I have a large number of conserved supercharges, I'm in a very restrictive quantum error correcting code where the number of logical operators that can take me out of my code subspace are quite limited, but the protection that the code affords me is quite strong. And as I break the number of supersymmetries to a smaller number of conserved supercharges, then you're afforded a larger amount of logical operations, but the protection that is afforded by the supersymmetry from a quantum error correction perspective reduces until finally you break down to n equals 1 or n equals 0 supersymmetry, at which point there is no residual quantum error correcting interpretation. So there's no protection, but of course, now the exchange that you have between freedom and security means that you now have freedom to do whatever scattering you want. So higher and better quantum error correction, fewer logical operators. Lower n, worse quantum error correction, more logical operations. And so thinking about things in this way kind of gives you a unifying picture that allows you to think about many different systems of interest that have superselection and high energy physics from a quantum error correcting point of view. And so, again, this is something that hasn't been plowed before. So maybe by thinking about things in this way, you can adopt quantum error correcting techniques to more novel parts of high energy physics. So I want to conclude by just listing some of the major questions that I want to consider, and I invite you to consider as well, with or without me. The first is we want a more general noise model. For holographic quantum error correction. The noise model that we had in this ADS-CFT picture that we made connection to the Hawking Page one was a thermal noise model. right? You could have more pathological noise that's not just that generated by thermal noise. So if you wanted to, for example, figure out how to be fault tolerant against arbitrary 1-qubit errors or arbitrary errors on some small number of qubits, you would need to find a more general noise model for these things. Holographic quantum error correction was kind of developed backwards compared to how most quantum error correcting codes are developed, where they're built from the bottom up. Quantum error correction, holographic quantum error correction was kind of built top down to fit an existing model. And so many of the questions, like the exact code properties of the holographic quantum error correcting code, are much less well understood than the ones that were developed for traditional quantum information. And that's solely a remnant of how it was developed. So this would be useful. The second thing is the thing that I said a lot. Can we prove some subset of a duality, either direction, between fault tolerance and threshold theorems and confinement deconfinement? UFTs. This would obviously, if you could prove this, give you a lot of interesting results. The third one is, can we use quantum information to understand the Sano Van Ramsdonk gap between Hawking page and confinement deconfinement? Maybe there's some way of using quantum information techniques to understand what that gap is. Perhaps, for example, when you're below both thresholds, you're definitely fault tolerant. When you're above both thresholds, you're definitely not fault tolerant. And when in the middle, there's some transition area. How do we precisely characterize the transition area? And then fourth, and maybe most ambitiously, can you ask questions about the mass gap by using ideas from quantum error correction or fault tolerance? And with that, I think I would like to thank you for listening to my talk, and I would like to take any questions that you have. Okay. Yeah, no, that's correct. But I guess I'm trying to be very conservative where I say that, like, had they done the calculation at exactly the same coupling constant or had a sharp argument for why flowing to the coupling constant that the Hawking page is normally calculated at, that they would hit it on the nose, then I would not be worried about this. But given that there was a gap in their calculation, um, and that it's possible that it won't hit on the nose when you flow to the correct coupling constant, then there's some possibility that they won't match. And if they don't match, then I would like to use quantum information techniques to understand why they don't. But they might match, in which case this is a moot point. No, definitely. So I'll add a note to my slides that this may already be solved. Yeah, I think it's definitely one, I think it's definitely morally related, and two, there's a reason why I wanted Keishiro to come and do a postdoc with me at Northeastern because I precisely want to understand this connection. Um, yeah, I think that there's clearly a relationship. I am a little bit concerned that those techniques are not general enough to solve this most general version of the question, which is not a criticism at all of their techniques. It might be that there does not exist a technology that's general enough to answer two in full generality. But yes, I definitely want to understand that connection better. No, I think that one of the reasons why I'm motivated to do this line of work is that I think time evolution in holographic quantum America codes is very not understood and in some sense very not well studied. And so what I'm trying to do is use what quantum information people often do when they try to ask the question of dynamics for normal quantum error correcting codes. Generally, when they ask those questions, they move to threshold theorems and fault tolerance. And so for me, I'm wondering if trying to understand the holographic interpretation of threshold theorems and fault tolerance will give us some clue as to how to better understand dynamics of holographic quantum error correction.